In this problem, we want to find the eigenvalues and corresponding eigenvectors for a given 3x3 matrix. So with the problems, as always, we start with looking at a minus lambda I and finding the determinant. So in this case, a minus lambda I just involves subtracting lambda off of the diagonal entries of this matrix. Just something like that. And now we can find the determinant. Now to find this determinant, we want to figure out the best row to expand along. And in this case, we want to expand along row 2 because row 2 only has one non-zero thing in it. And so the determinant of a minus lambda I will be given by expanding along row 2, meaning the only entry we care about is row 2, column 2, negative 1 to the 2 plus 2 times that 1 minus lambda times the determinant of the remaining 2 by 2 matrix, 5 minus lambda minus 6, 2 minus lambda. We can compute that 2 by 2 out. 5 minus lambda minus 2 minus lambda plus 12 is just AD minus BC. And then we can expand out that quadratic inside the brackets. We get a lambda squared. We have a plus 2 lambda from these two terms and a minus 5 from these two, so that's a net minus 3 lambda. Minus 10 plus 12 is plus 2. And this factors as 1 minus lambda and then times lambda minus 1, lambda minus 2. So what we have here is negative lambda minus 1 squared, lambda minus 2. So we have a repeated eigenvalue of 1 and then another eigenvalue at 2. So let's do the easy one of these first. Let's do lambda equals 2. Looking at lambda equals 2, we want to subtract 2 off those diagonal entries, which gives us a matrix that looks like 3, 6, minus 6, 0, negative 1, 0, 2, negative 1, negative 4. We now want to row reduce this, so I'm going to divide the first row by 3 and the second row by negative 1. 1, 2, minus 2, 0, 1, 0, 2, minus 1, minus 4. We are then going to reduce this by row 3 is row 3 minus 2, row 1. First two rows stay the same, and what's left is 2 minus 2 is 0. Negative 1 minus 4 is minus 5. Negative 4 plus 4 is 0. And then I can do row 3 is row 3 plus 5, row 2 to get rid of that minus 5 as well. So thankfully, as expected, we have a row of zeros here at the bottom of the matrix, which we expect to get for our eigenvector problems. We can now figure that's what we get for a vector. So in terms of equations, this says that v2 equals 0. v1 plus 2v2 minus 2v3 is 0. Well, if v2 is 0, that term's also gone. And so I have v1 equals 2v3. v3 is a free variable. I can pick v3 to be 1 and v1 to then be 2, with v2 being 0. Means that for lambda equals 2, an eigenvector that we get here is 2, 0, 1. Great. Now let's look at lambda equals 1. Now I want to subtract 1 off the diagonal, not 2. And if I do that, I will see a matrix that looks like 4, 6, minus 6, 0, 0, 0, 2, negative 1, negative 3. You want to row reduce this. So I'm going to swap rows 2 and 3, put the zeros at the bottom, and then divide the first row by 2. I could divide row 1 by 3. I could divide row 1 by 2 if I wanted to, but I'm not going to for the sake of making this shorter. I'm just now going to do row 2 is row 2 minus row 1. 2, 3, minus 3, 0, minus 4, 0, 0, 0, 0. And then dividing row 2 by negative 4. 2, 3, minus 3, 0, 1, 0, 0, 0, 0. It's now in a good form. So again, as equations, we have that v2 must be 0, 2v1 plus 3v2 minus 3v3 is 0. v2 is already 0, so that's just gone. 2v1 is 3v3, so I can set v1 to be 3 and v3 to be 2. Which with v2 being 0 gives me my eigenvector that I want. For lambda equals 1, the vector that I get is 3, 0, 2. Now, this is the case of a repeated eigenvalue that is defective. And what that means is that I only got one eigenvector here, but the eigenvalue 1 was squared in the characters polynomial of this matrix. So that means this is a defective eigenvalue, and we'll have to figure out how to deal with that later when we get to the VQ side of things. But at this point, that's all we've got. We've got our two different eigenvalues at 2 and 1, and then each one only gave us one eigenvalue, one eigenvector, and that's fine for the setup. That's what we got. So we have lambda equals 2, an eigenvector at 2, 0, 1, and lambda equals 1, an eigenvector at 3, 0, and 2.